The Wall of Wind, the WOW, is a state-of-the-art hurricane engineering research facility at Florida International University. It is a legacy of 1992's Hurricane Andrew that devastated parts of South Florida and led to the creation of FIU's International Hurricane Research Center to mitigate wind damage. The Wall of Wind's evolution has made it a unique testing facility that, since 2012, has been capable of simulating hurricane effects, including from Category 5 storms. After becoming one of the major experimental facilities under the National Science Foundation's Natural Hazards Engineering Research Infrastructure, or NHERI, the Wall of Wind has developed a wide external user base. The facility supports the user's fundamental research on wind hazards affecting homes, businesses, and infrastructure. The vision is to enable frontier research and education to prevent wind hazards from becoming community disasters. The WOW is located at the FIU Engineering Center in Miami, Florida, less than a mile away from FIU's main campus, home to the National Hurricane Center, Miami's National Weather Service Forecast Office, FIU's International Hurricane Research Center, and the Extreme Events Institute, which oversees the Wall of Wind program. Within its 72,000 square foot area, the Wall of Wind deploys the latest technologies in hurricane simulation and damage mitigation research, both critical for achieving hurricane-resilient coastal communities. The WOW's 12-fan system provides controlled, programmable, and repeatable large and full-scale testing in flows that efficiently replicate wind speeds to 160 miles per hour accompanied by wind-driven rain. Users enter the facility through the Operations and Control Center, a 1,300-square-foot air-conditioned space where the team operates the Wall of Wind fans and data acquisition systems. Telepresence capabilities also allow users to remotely view the tests in real time while virtually interacting with the EF technical team and providing feedback during the experiments. The facility's cutting-edge instrumentation includes Cobra probes and a tomographic particle imaging velocimetry, or PIV system, to measure wind field and flow characteristics, a Scanivalve pressure measurement system to record wind-induced pressures, single and multi-axis load cells to measure forces and moments, accelerometers to capture vibrations, and strain gauges to monitor material stresses. A robotic arm is available to set up instruments and precisely map the wind field at the test section. The data acquisition is based on National Instruments' Compact Rio system with a custom-built LabVIEW software and a modular DAC system from GraphTech. The 12-fan system is housed in an 8,000-square-foot building. Fan motors have a combined maximum power rating of 8,400 horsepower. Variable frequency drives, or VFDs, allow fan speed to be regulated. Multiple fail-safe and human safety devices are located throughout the facility to monitor the fan system performance and ensure safe operation. Users can take advantage of a combination of elements to create different wind characteristics to satisfy their testing requirements. The short contraction section boosts wind speeds to 160 miles per hour and above. A 30-foot-long rectangular flow management section provides the required fetch length. Adjustable spires and automated floor roughness elements generate atmospheric boundary layer wind flows with turbulence for various terrain conditions. Different numbers and types of water nozzles are used to generate wind-driven rain conditions at various rainfall intensities and raindrop size distributions for water intrusion experiments. The open jet test section is 14 foot high by 20 foot wide. Test specimens can be placed on the 16-foot diameter turntable located downwind of the flow management section. Manual or programmed rotations through multiple wind directions simulate directional wind effects on models. The pit underneath the turntable allows users to place data acquisition devices directly under the model where they are protected from the wind and rain fields. Lights and cameras are located on masts at either side of the testing section. The remotely operated high-definition cameras capture live streaming of tests, allowing for viewing, remote monitoring, and slow-motion replaying of failure or damage mitigation and propagation during tests. Downwind of the WOW building is an open area surrounded by safety netting and a 15-foot-tall debris wall, which prevent debris from destructive tests from escaping the facility's secure area. Adjacent to the wall of wind building is the 3,000 square foot Staging, Construction, and Instrumentation, or SCI building. It houses a tool room, a fabrication shop, and small-scale wind tunnels. Here, test specimens are constructed and instrumented before being moved to the WOW test section. This way, multiple users can utilize various EF resources simultaneously. For example, one user can construct and instrument a test specimen in the SCI building, while another user is performing tests in the WOW building. The WOW building has an overhead gantry crane capable of lifting models weighing up to 5 tons. EF technical staff inform on-site users about safety and emergency policies and provide safety training on site access, personal protection equipment, and operation. The EF team assists users with test protocol implementation for aerodynamic, wind-driven rain, and failure mode testing. A full suite of services provided to EF users includes assistance in NSF proposal development support, test planning and budgeting, specimen construction and instrumentation, test execution, high-definition video imaging, data acquisition, data quality assurance, data management, and post-test specimen removal. Users are supported with EF software application and specialized data analysis if needed. If necessary, users are provided access to office spaces and business support services. User data packages are archived and uploaded to the NHERI Design Safe Data Repository in compliance with NHERI cybersecurity policies. EF data reuse by other researchers is actively encouraged. Payload opportunities are also present. Most recently, the WOW has expanded its capabilities to include a unique large-scale downburst simulator to enable EF users to study the effects of non-synoptic winds on structures, and a distinctive high spatiotemporal resolution PIV system to enable whole flow field and fluid structure interaction characterization at high Reynolds number. The new capabilities greatly enhanced WOW's national NHERI EF standing and expand its science plan by allowing high-fidelity measurements to help a broadly inclusive external user base to obtain data for validating computational simulations. The WOW facility empowers the educational experiences of K-12, undergraduate, and graduate students in STEM-related fields. Educational activities include hosting external students for hands-on training under the NHERI Research Experiences for Undergraduates program. School teachers are engaged in the Research Experience for Teachers program to translate new knowledge into classroom educational materials. Overall, the NHERI WOW enables advancements in natural hazards engineering by providing a unique test bed for cutting-edge cross-disciplinary research and education. The mission is to significantly improve design practices and foster transformative hurricane mitigation measures for buildings and lifeline infrastructure. This unique facility allows users to achieve technical breakthroughs and help build resilient and sustainable communities.